So, good morning. So this is day 3 of building the basic neural network using Python without any libraries like TensorFlow or PyTorch. So I'm going to start off by just looking through what I have so far, because I've had a hard time solving the backpropagation, which is the hardest part. I will finish this. I will finish what I started. Okay, so up here we import the libraries we need. Take a look at the data set. We split up the data into attributes and labels. Print out the shapes. So here we define static methods. Let's call them. Here we're gonna add one more markdown for layers. Basic layer class and class called layer. Extend. We can also add a to-do here, where we could add what we could do is to create an interface for the layers. Since this is markdown, I think we can make a checkbox. Maybe we can't. Oh. Okay. So let's see what we have here. So we ended up connecting the layers in this way. So a layer can point to the previous layer and the next layer. So basically, we have our network here. We have our inputs. Then we're gonna have one hidden layer of 4 neurons, one layer of 2 neurons, and one layer of 1 neuron. So the first one is input layer. We have one hidden layer, second hidden layer, and the output layer. So this layer, the input layer, has to point to the next layer. Wait, can I rotate this somehow? Oh, okay. So the input layer points to the first hidden layer. First hidden layer points to the second hidden layer, and the last hidden layer points to the output layer. Just gonna move that a bit. Beautiful. But then also for the backpropagation, it comes handy if we can also look in the other direction. So the output layer points to the layer before that. Well, you get the point. Like this. Basically, let me move this a bit. this way is forward propagation. I'm gonna decrease the size of that a bit. Beautiful. Then we also have backward propagation. That goes in the other way, other direction, like so. I think this explains it quite well. So for propagation, this is where we predict things. And this backward propagation, this is when we adjust the neural network, basically when we train it. Let's add a box around this. Beautiful. Okay, so that explains these two. We can actually add comments here. So the prev layer is used for back propagation, and the next layer is used for forward propagation. Let's flip those around. So get identity is just a simple helper function. It's to easily print out the identity of the layer. It's used for debugging, for instance. So this is what I was working on last time. We're gonna get back to this. So let's save that one for later. We also have to set the input shape of each layer. And the input shape, see, should be right. One more rule I got it right down here is that instead of using the indices as rows and columns, I'm using them as columns and rows. So basically, what this means is that if we assign an array like this, oh, that's too thin. Okay, we have this array here. Find it as 1, 2, 3. Then what this really represents is this. You know what, we can remove those. Okay. So that is important to keep in mind. I did a mistake where I forgot I was doing this yesterday, which cost me some time. An hour or two. Welcome to the stream, by the way. So, I was saying, this is where to find the input shape of the current layer. And the input shape has to be adjusted, as we see here. Since if we look at the math here, oh my god, my paint is, whoa, sorry, I hit the Visual Studio. Okay, anyway, so let's look at some of the math to understand why we have changed the input shape in this manner. So assume we have a an input here. You know what we have? let's go back a step. So the math behind the layers is the following. We have the what do you call it? The pre-activation function. This multiplies some weights with an input. Let's call it input A, and add a bias to it. So keep in mind all these are matrices. Then we take the Z, plug it into an activation function. Let's call it, I don't remember the name of this character, but you know, that character. Right, and we plug in Z into that one. Both. So the A up here, this A, is the A from the previous layer. That's the output. So this will be the output of the layer we're looking at now. Let's go back. Okay. So since the input layer does nothing specific, it just passes on the inputs. If you look in the code here on the input layer, we see it has a for function, which only returns what's in the next layer. So basically, it just passes the inputs forward. Okay, so if we look at the first layer, we can do that here. First, you know what? Let's just write input layer. We're gonna add a box here. We're gonna do the math down here. Okay, so this is the input layer we're talking about now. Okay, let's leave it like that. So, see here, we have 4 inputs, which means that our input, let's call it A, has 4 values. A1, A2, A3, and A4. This is a matrix. Poof. Now, the way neural network works is that each neuron here, each of these circles is connected to each of the inputs. So basically, we can draw some thin lines here. Describe this. Okay, I guess you can see these. Super thin, but you gotta be able to see. Okay, oh, that's too thick. So this one is connected to that one, that one, that one, and that one. But this neuron up here is connected to all of these also. I guess you see the pattern here. And if we look at this one is connected to all of these. And this one is connected to these two. And so on. So it's basically just, it's a web. It's like a huge web of connections. So you can say that the layers in the middle, the hidden layers, they're kind of too complicated for you to understand what's really going on at its whole because it's so much math at the same time. So since this layer has 4 neurons that each take 4 inputs, it means that the weight matrix is a 4 times 4. Okay, so we're gonna add superscript here, by the way. Well, let's call it a 0. Yeah, for now. Then we have the weights. This will be belong to the first layer. So basically this layer has index 1. 0, 2, and 3. So this will be a 4 times 4 matrix. Running it out will take some time, so I think I'm gonna do that. I'm gonna let's see, what am I gonna do? I'm gonna look at the code here to see how I decide to do it there. Okay, let's yeah, so wait, does it work like that? How we write this? I think what we'll do here we have the weights for the first neuron transposed. Transposed basically means that you tilt a matrix. So this matrix here, A transposed, would be horizontal, not vertical. So 2T W 3T, we have W 4T, and that's it. And let's see, let's check like that. Yeah. So after written it like this, we know that the basic way it's written. If we skip the transpose, it's basically a column here, the weights for the first neuron, second neuron, third neuron, and fourth neuron. I know this looks horrible, but I do my best. Okay. Maybe it's a bit too big now. Welcome to the stream, by the way. I hope you're having a nice day. So, let's see. When we generate the we set the input shape, we also at the same time generate the weights. Meaning, since we know the shape of the weights we're gonna have, that also means that that doesn't mean that we know the shape of the input, because these two can be different. 1, 2, 3, 4. So I got to do some math in my head here. So the progress isn't great. I managed to get the forward propagation to work, but not the back propagation. Hold on, just gonna lower the volume a bit of the music. So basically, I don't know if you're familiar with the math behind it, but it's kind of simple, but at the same time, it's not. Like the concepts are so big, it's hard to implement them. So right now I'm analyzing the code I have so far and trying to figure out what the thought was behind each line of code. So we have this function, set input shape. This is used when adding the layers to the model. Let's take a break from the analysis of the code and try running it, see what happens. Also, maybe I should clear up some of the printing I did yesterday. Oh yeah, I did that for a course actually a few weeks ago, but we only had to do it like one step, so I don't feel like I fully understood the concept. Well, the concept, yes, but the math behind, like what happens when you go back multiple layers. Did you pass the exam, by the way? Ah, good job. And did you get the back propagation right? Luckily. Yeah. So I assume you're still a student then? What are you studying? Mm. Mm. Nice. I'm personally studying information and communication technologies. It's similar, but there's a bit more physics to it, and the physics part of the program taking it's not the part that I'm enjoying. It's the physics is a boring part, because that's not why I applied for this program. I won't do the software part and the math. But I think I've completed all of the physics courses now, at least. Oh, one more person joined chat. Welcome. But how much is left of your studies, by the way? Just 2 months. Then you're almost done. Congratulations. So is that is it a bachelor or is it a master's? Good job. Good job. I'm gonna apply for master's after my next year when I complete the bachelor. So, by the way, if you have any cool projects, like AI-related projects or games, that's public, I would like to take a look at it. It would be fun to see if you have a portfolio somewhere. Let's see. Where was I? Okay, but is the hobby project public? Maybe I can see it if it's uploaded somewhere. I understand if it's a secret. You don't have to share it with me. It's just I'm curious. Okay. Well, maybe you can get back to me when you publish it. I would love to see it. Let's see. Okay, I understand. But might still look great on your resume later on. But you got me curious what it is. Haven't you done any cool projects during your years as a student? I decided to learn Rust, so I started separate. Oh, okay. I've heard great things about Rust. Haven't tried it myself though. Cool. Robot arms. That would be fun to try program. What did you use for that? Was it Python or C maybe? I hope it was in Java. I'm not a big fan of Java. C++ and Python. Yeah, makes sense. There's always Python involved. Let's see here. So let's get back to this. So the math for the input layer is very straightforward. There's nothing extra we have to do with the input layer. With the like basic input, but there's some stuff we gotta do to make it work on the second hidden layer when we pass it there. The second hidden layer only have 2 neurons. Oh, by the way, before I continue, make sure to follow, I guess, if you want to. If you enjoy watching me struggle with this, it can be pretty fun sometimes. You know, see other developers struggle as well. So it makes you feel better. Okay, so as I say, it has 2 neurons with 4 inputs each. So the shape of this would be... Wait. Would it be this shape? One row per neuron, I think. 1 column per input. Ah, thank you. Whoa! I hope the work goes well also. And you're feel free to stay on the stream. Just enjoy the vibe. And if you get stuck, just focus on the stream a few minutes and watch me be stuck as well, and probably feel better from that. Okay, so I have the inputs here. It is like that, but right. Should I transpose the inputs? Each one row. And first and second one. This is wrong. We have... Is it this we have? I have confused myself with what's transposed and what's not transposed. The whole system that I used columns for rows. Maybe I should go back and fix that. Might be a good idea to solve this confusion. That means we're gonna go to predictions, and when we predict, we take an array of a 2-dimensional array with each row is 1 input. So basically we can send multiple inputs and receive them back predicted. So create a empty result array, and we append to it what we get back after I've passed in the input into the input layer. So if we transpose the input here, we actually convert it to this format. So let's add a comment here. To make it a column vector. Okay. So now we fix that. Meaning if we look at the sorry, my throat. by the way, let me know if you want me to increase the volume of the music. Okay, so we have we have this input. I'm gonna check the weights, how we create the weight matrix. That's done here, where we set the input shape. But do we need to set an input shape though? So now we do set the input shape. Let's leave that in there for now. We assign weights equal to this dimension that uses the input shape as one of the values and of neurons as the second one. If we... Okay, so I'm just gonna run this. It's gonna give us some errors, but that's fine. Because we're gonna look at the second layer. You know what? We can reuse this. We can move this code up here. And look, next layer, input layer, next layer. So basically now we're looking at this one, the first hidden layer. That one. Maybe we should, so see the indexing here. It's not the same as one in the drawing, so maybe I should, I could fix this. I could just decrease these indexes. Self, layer mount, +1. There we go. Now we have indices that are same. So input layer 0, first hidden layer is 1, second hidden layer is 2, output layer is 3. That's good. Just gonna see what my family wants to say. They're spamming me right now. They're fine. So we look at the first hidden layer then. Print out the weights. Get this. It's hard to tell by the shape if this is correct or not. So I was thinking we could hide this one. Let's not add that hidden layer for now. Or we can look at the second hidden layer. So you type next layer, weights. If you go here, we're gonna add one more layer here. So hidden layer 2. We know that the output is of this shape from the previous layer again. Let's see, 1, 2, wait a minute, hidden layer 1. Right, yeah, this is damn. this wrong. This is not the input layer. The input layer doesn't have any weights. I'm sorry about that. So let's move this up there. This is the first hidden layer. And this is the second hidden layer. So the output we get should be transposed. We gotta make sure that it is that. I'll be right back. I gotta use the restroom. Okay, everyone, I am back. Maybe I should do something about the chat being hard to read while I'm at it. Let's see. Can we maybe add a color solid or something? Or just change the look of the chat box? Let's doesn't want to collaborate with me. It's I think I can copy the chat box design from another scene. Nope. I cannot. Well, that's annoying. Let's continue anyway. So hidden layer 2. Should be weight should be of. Is that the right shape? See, I'm just gonna Google this. Honestly, it's better that I do that. Okay, just got a request. That should fix the chat. Just gonna write a test message here myself. Yeah. That's close to impossible to read. Let's see. Modify image color block. There we go. Make it just like that. I'm gonna place it behind the chat box. Something like that. Let me make it a bit transparent. I think that will do for now. Yeah. I hope you like it. So, right, I was gonna do a Google search. Maybe I don't have to. I actually have some material from a course I just finished. Let's open up a incognito browser here. So this was the first presentation about neural networks. So this was actually for the second AI course I took. Okay, so we have our weights. Okay, so you see that they are vertical. They're columns. One column per neuron, I guess. Yeah, one column per neuron. I'm gonna go to this function. One column per neuron. Okay. So if you look here, we can ignore this one. This one's basically for the output layer. It has to be treated a bit differently to work, at least when I wrote the code yesterday. Let's see. So if you look at this matrix, so now we are thinking rows then columns, not the other way around. So now we're doing it properly. Proper. There we go. So we can, that means that we should have, let's see, one, like I said, one column per neuron. We should have two. Basically, like that, I think. Because those transpose, so they have been flipped. Yeah. So this should be right. Thus, what we want to see here, the first one is rows. Yeah, this is correct then. So a row and column. Yeah, this is right. If we look at the weights then for the last layer, we can actually just type last layer since we keep track of that. This means we have one Vilket gulligt meddelande, älskling. Det är så sött. Sötis. Hoppas din dag går bra. Okay, so we will go back up to where we assign the weights. Focus on how we do that for the output layer here. So we flatten it. I'm not sure why we flatten it. Maybe we can. We don't need to flatten it. Let's comment this out for now. Let's treat them all equal. Okay. We will then see. Okay, so the weights now for the oh yeah, they should be right. Okay, so let's add some text here for the output layer. The output layer should get an input of this shape. A1, A2. Since the output layer is only connected to these two neurons. That one and that one. And then the weights. So W superscript 3 should only be one column. That's what we got, as we can see here. So first rows, then columns. So row 1, row 2. Okay. That means, so the calculation here would look like this. So we would have Z3 W subscript 3 transposed dot product A subscript 2 plus its bias. Let's see, is this correct? Yes, this is correct. So we're gonna check this shape of the bias here. And we want that to be just an array with just one number, really. Because this is basically equal to A1 plus B2 A2 plus B superscript 3. This is integer. This also has to be an integer then. And welcome to the stream, by the way. I hope you're all having a very nice day and enjoy watching me struggle with this code. So let's see the shape of this bias. Yeah, but it is one-dimensional. Maybe that is fine, because we will always. Yeah, it should be one-dimensional, I think. Let's just see where I add the bias. Just sure. Yeah, one bias per neuron. Enjoy it very much. Let's see. So we checked that. I think the predictions might work now. No, they do not. So we have an error here. This is in the prediction function or prediction method. List object has no attribute C. Yeah. Wait, what? So that's it. I think we can convert this list into a NumPy array. Then we can transpose it, I think. And create another variable, prediction. Move this here. There we go. So first we find transpose, then we send it into the input layer, then we append result, and lastly we convert the list into a NumPy array and flatten it. Maybe. Yeah, worked. So if we run this multiple times, we get different results. Right now just a bunch of zeros. Huh. Ah, there we go. So that will be fixed probably during the training. So basically during the backpropagation. Okay, so just looking at converting inputs. But we're gonna skip that for now. But before we move away from it totally, we will look at the function I wrote for it. Convert input. Yeah, so it would to simplify how we write the code for the calculations during midterm predictions. Wait. Do I ever use it? No? Okay, forget what I just said, and we will see what happens when we try to fit the model. So fitting, that is the there's a training of the model, and it includes the backpropagation. You will see how we print out some information about like which layer, what's going on there. There's no spacing here. We want to add some a blank line here so we can easier read it. Let's just copy this and see where that is in the code. There it is. Just do like that. Should be fine. Maybe this can be printed as a one-liner. Let's see if Copilot has anything to say about it. What? Okay. Let's just forget I even tried. So, this is a bit clearer. So, notice how we start off by looking at the output layer. It's because the back propagation is going this way, from right to left. And we take this output layer has input shape 2. The inputs it was given is this. The loss gradient is that, self-calculate is okay, so do you implement back propagation in one go or per layer? That's a good question. The goal is to do it. It will be done per layer, I think. But like I adjust the weights and biases of the output layer into hidden layers without. Oh wait, how do you describe it? Okay, basically I store all the data I need in each layer, and then I start the output layer. I adjust the weights and bias, and then adjust the same weights and bias on the second hidden layer and then the first hidden layer. So I guess in one go, I think. But you can, because changing the weights and biases like all at once or one at a time doesn't really make a difference, does it? Ah, right, it shouldn't make a difference. So, yeah. Which way would you recommend, though? Ah, probably, yeah. I guess. Wait, when you do it in one go, you have to store all the new weights and biases a while before you apply them. So then I guess I do it per layer. Because if you look here, when I do the backward propagation, I call the backward propagation for that layer and adjust it, then I pass the new loss gradient to the previous layer. Perfect. Thank you for clarifying that. Ah, perfect. Let's add a comment about that. There we go. Thank you so much. So, yes, it's time to look down here again. The output layer has input shape 2, yes. Its inputs are 0, 0 that was given, sure. That's okay. Loss gradient is freaking huge. Self-calculate Z. It's that. Okay, so that's the pre-activation function results. Hidden layer 2. Let's see where things go wrong. So we have our 2 neurons with 4 weights each. We have the inputs it was given. So this input was basically... Wait. I'm missing something here. No, I think that's correct. Let's give those inputs as neutral loss gradient, self-calculate Z. Okay. So the problem occurs when we try to up the bias gradient. We multiply the inputs, or we subtract the inputs by the loss gradient. That should be fine, because loss gradient is just one value. Then we try to multiply, so maybe this should be dot product for 2 wait. Okay. This math is a bit weird. Let's clear it up. It's hard to draw in paint with a a mouse. Maybe I could... I have one of these old drawing pads, but I don't think there are drivers for it anymore. Maybe I should check it out. So it's a Bamboo Pen CTL 460. Drivers. What's that? Oh. Haha, cool. So this is local storage. Yeah, maybe this is better. You use it for your studies? And can I select stuff? Oh yeah, I can. Huh. That's neat. Let's see if you can combine that with the drawing pad I have. I can move this. Ah, okay. I used to work with OneNote, you know, Microsoft's program. It was pretty good, but for some reason it became very heavy for the device to run after a while. And I think it has something to do with the resolution shows before you started like drawing on it. Okay, I'm installing the drivers now. This is dark mode. Oh! Nice, dark mode would be nice. Okay. I'm gonna try connecting the drawing tablet now. Okay, okay. See, oh my god, it's working. But I have to change the settings. Oh my god. Oh! I don't think it came with the software. It did! Oh my god, okay, so I bought this tablet like, I think I was 14 years old, so it is 14 years old then. Let's see. Tablet, left default. Mouse mode. Maybe we can map it to monitor 1. Then if I move it around, oh yeah, much better. Let's also try the website you sent. Whoa. Yeah, that's better. Can we... Oh, I can just change stroke with. Very light and press harder. Oh my god. It has support for that. Nice. Okay. You said it had dark mode? Maybe we should use... I want to use a yellow... Oh, maybe not the yellow one. This dark mode in the menu under themes. Oh, there it is. Perfect. Yeah, I found it. Thank you. Can I mark this one too? Okay. So I'm gonna save this one for later then, so we have this program now. It's an upgrade. Thank you so much. Okay. We have the bias gradient, self input. Okay. See if we can draw the math here. So right now we're trying to... Oh, that was big. Basic control A, select all and control C. Oh, okay, okay. This is a pretty decent tool. Let's have control Z. Yeah. Cool. So take 2. I'm not used to this. Okay, so I have 2 inside here. We have self input, which is... Wait, the input is not transposed. So right now we have an input of 1, A2, A3, A4. Can we expand this? Oh, yeah. Okay, oh crap, I hit the formula. I hit the error. Where's the error? Let's work up here instead. Yeah, that's better. So we have this minus loss gradient. So minus the loss gradient is that. So let's call it just L. This is then multiplied, which should really be dot product. Let's do dot product for now. With the post activation function, which is this shape. So I'm thinking, shouldn't the self.inputs look differently? I'm not a big fan of this lo-fi right now. Yeah, so the input should be of this shape, which is not. So let's look into that. Or save the input. Well, let's print out the transpose input here, just make sure. Print transpose input. So transposed, that's not transposed. Wait. And if we call it not transpose input. Just copy that. Why is it not transposed? Wait, do we create an array? Array, do you even convert like this? Let's be lazy. Transpose. What happened with it just dot capital T? Let's try this. Alt TMP. Print TMP. Also print T. Last we print TMP mp.transpose TMP. Okay. So the transpose doesn't do anything right now. And so this would have to be basically cloned. Because if it had I think this should be following 2, 1, 2, 3, 4, and then the same again. So we would like copy this to make it fit, since this is the real input, I think. So minus L dot product Z1 Z2, but also that is that correct now? When we did a prediction here, we have one variable. Let's see if we can follow the outputs of the layers, like step by step. See how the data is formatted. So that's the first output, second output, third output. But these aren't transposed. Um, so when transpose it, there's no difference. So I think that means that the also built-in dot product function takes this into consideration. Meaning we can can we just take the input here, pass it into the prediction? I think so. Yeah, it works. So basically we don't have to worry about the transpose unless we have more than one dimension. Okay. I can live with that. Then that's okay. We can hide that again. Should be fine. Print self, and also that one. We have this again. So I want to see where we perform the math. The dot pattern prediction. That should be done in calculate Z. Yeah, there it is. So let's print this out. So weights is transposed. As it should be. But inputs isn't. Inputs is. Okay. This would work. Would this work? Yes, it would work. It would work too. Oh. Let's see. For debugging, you can use print f blah blah some order some field do print blah blah. Let's try that. I'm gonna try what you just wrote, which is here. Wait, don't you just... So F is for formatted, I guess? But should there really be an equal sign there? Isn't it just like that? You want the equal sign at the end, okay. What does the equal sign do? Alright. Oh wait, shit. Okay, I get it. I messed it up. Ah, there it is. That is nicer. That's some good advice. Thank you. I'm gonna remember that. I'll put another context as prefix or postfix, I think. Okay. So you just basically add it before or after the curly brackets then. I think I'm gonna have to start heating up my lunch. Just give me a moment. Okay. It is a simple interpolated string. So I'm gonna set the timer here so I don't burn the rice. Okay. There we go. So, oh, I forgot. By the way, how do you make a new line for the printouts? Is it an L and G? Yeah, backslash N, that's what I thought, but... Wait. Oh my god, what's going on? Should be. And it was. I wonder what I wrote the other day when it didn't work. I was like, what? Thanks. You are my savior today. So have those. That should be the math. Should it? Those products per neuron. Would I have to transpose that? This should be fine if you manage to fix that. Poof, poof, poof. Okay. I think we should adjust how it's I think the input it stores, if it should be formatted right away. Backward input. So pass it input layer forward. The string calculate said that we store it, I think. Yeah. We take the inputs. Maybe if we input shape should be that. So convert it to the input into the input shape. Do I have to turn it into a list? I think so. So the error occurs in that layer. Right, in layer 2. Okay. Go to output layer, previous layer, and check the input shape. This is the input shape, but the does it have stored input now? No, it doesn't. So we can probably take an input. Wait, did it have? Yeah, this is what I'm looking for. So this should give us that. I hope. No, it does not. List already cannot be interpreted as an integer. Okay. Let's look up the function. We had to turn that into an array. Oh no. Let's start. Oh, okay. MP dot tile. So what would this give us? Okay. So I guess it would be the number of neurons. And that means it's just the input shape. Do you ever use input shape? Turn into a list. Why not keep as an? Maybe that's fine. Input shape. That's not how you do that. That's like an array. Okay. Seems to have worked. So let's look at how we store the input shape. Set input shape. That. Wait. What's going on here? I have some weirdest logic. So I think the input shape can also be the amount of. No. Okay, so get the output shape from the previous one. For the first layer, that would be 4. Is a layer class in your case a simple linear layer? Yeah, I guess it is. I think so. Set the input shape. The layer. Blah blah blah. So that's output shape. Yeah, that makes sense. So we take the input shape times neurons. Yes, that's correct. So you get the input shape like that, and I think we're just gonna get the shape of that. Input shape. There it Discord input. Sure. Let me double check that actually. Like, when you say simple linear layer, do you mean like just one dimensional? Like it cannot be, it can't take multiple channels of data? Yeah, that's linear layer. Wait, so linear layer is like just a dense layer basically, right? So it's not another type of layer, I guess. Yeah. It's supposed to be at least. If it is, I do not know. Wait, or fully connected layer. Damn, I forgot about all these terms. That's the same thing. Oh yeah, okay. Thank you. You got me really confused there for a second. Yeah, so it's fully connected layer, yes. That is correct. In the case, you need to keep track of the input shape, isn't it applied? Hmm. I guess it is. So maybe keeping track of it isn't necessary. I will try to show you the problem here that I face. So when I try to do the back propagation with this line, this math here, I end up with this, which obviously doesn't work. So I was thinking about expanding it to this. So the input will be or to this, since this A1 is connected to both Z1 and Z2. What do you think? Yes, it's a dot product. And what do you think about that? The order is wrong. Like this one's supposed to be vertical. We can transpose that with T if that's yeah. But this also has to take this shape, because otherwise it doesn't work. That's what I'm trying to reuse the shape for. I'm not even sure this formula is correct. I'm still a bit lost with the math behind backward propagation. But let's give it a try. Okay, so we transpose that. Let's do the dot product, but we're also gonna have to fix this one. Self input and wait. Let's not do anything stupid now. Okay. I just broke something. Cool. So what do we try to do now? We have the inputs. Try to let's refer to them as 0 and 5. That will be turned into minus the loss. I only have one number. Something is very strange here. Okay, so it's final time for lunch. I think I'm gonna watch a video on this while I eat my lunch. I've already watched multiple ones, but I think it would be nice with some repetition. Let's see. I'll be back in a minute. So where I think I go wrong is this formula. So I'm trying to calculate bias. Let's reverse what I did up here. Let's remove this conversion. Just to see the outputs. So on top bias, there should only be one bias, but we have two inputs for the output layer. I just noticed something here. While I was double checking the math. Apparently, I never insert the stepper function here. But that doesn't really solve the problem, though. Okay, I'll get back to eating. Welcome to the stream, by the way. I'm just about to finish my lunch, so just sit back and relax while I do that. Okay, I'm done. Thank you so much for waiting for me. So... I'm trying to calculate the gradient descent, right? Move away the microphone a bit, decrease this volume. So we have bias gradients. Just for fun, let's print this one out. That's not how you write it apparently. Let's see what was recommended in chat. F. Oh, oops. There we go. And the second one here, like so. Give him a bit more space. So the weights, that's not right. Wait, or gradients, maybe it is right. I guess it is. So, bias gradient. Let's see. See if Copilot can figure it out. Probably not. Is that shapes of arrays are not aligned with the upright? You don't say Copilot. Right. Did it even do anything? It's the same thing. Okay. So they use the same loss function. That's good. All search are done. No, that's propagation. Yeah. You want to minimize it, obviously. Okay, so write our loss function in a simple way. Yes, that's fine. X and Y are input data that is constant. Value A divides B partially. Yeah. Zoom in a bit. All these damn ads. It's too much. There we go. Descent with respect to W. I found something completely different. Wait. Where's my paint? Where's my paint? Wrong paint. I found this. Two times a minus y, so the predicted minus that one. But then also divided. Not the stepper. Wait, I have the reload. Do I have to add that? The CDA. Oh crap. Yeah. I think I done a mistake here. Big ass mistake. So I would still X. I ended up with A. Something's wrong with my math. There shouldn't be an A there. There should be. Oh, I can call it Y hat. So I think. Try to draw here what I think we are looking for. believe there is this, that del C del V in our case in fact is equal to 1 divided by n times predicted values, let's call it y hat, minus y times the inputs to A times, well, actually it will be, those will be two vectors. But then also, what happens with the activation function? What would be inside step? There put Z, and Z would be as input, as bias. X is input. Yeah. Then for del C del V, this would disappear. Dobby. Maybe. But will this work? If we use a vector of, let's say, 10. We do dot product. That's no. So what happened with the activation function? So we have yp and y. This predicted and this true. And they only give us, wait, that's a vector. So those two turn into an integer. But okay. Sure, suppose. So what confuses me is that. Just for a okay, so find the average of it, I guess. Poof poof, divided by 10. Then we get the gradient. So right, they refer to the cost function as J. I refer to it as C. And they put it back in there. Can they really do that? Because they claim that this is equal to the original. It's not. Why? Okay. Great, using. Okay. Try and find some comments. Okay. So what confuses me is this math that did appear. This. Because by writing it like this, they claim that this part is the same as just the original cost function. and that'll happen to the activation function. No, the gradient is multiplied by the income value of x. The income, yeah. So the overall value 0. I fix the derivative of ReLU here, but that's not the problem. My Chrome is crashing. Crap. There we go. I'm gonna have to reopen the tabs. Once again, they claim this is equal to J, but it's not. pause the music a while. I'm gonna look for not video, that video, but this one.
Visste du att solens UV-strålar kan vara skadliga och åldra dina ögon i förtid? Vi hjälper dig att hitta solglasögon som skyddar dina ögon bäst. Välkommen till Synoptik. Kom och njut av sommaren med Donken och Elmar.
So much ads all the time.
Which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative gives us the sensitivity of C to small changes in WL.
Let's compare a bit. So,
We found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to examples.
Out of all training examples. Okay.
And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just the sensitivity to the bias, for example, is almost identical. We just need to change out this del Z del W term for a del Z del B. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of Z to the previous activation, comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an function is to
So, okay, Chrome is not behaving well today. We send the new gradient forward somewhere. Okay, my computer is sliding like crazy. I gotta see what's going on. Okay, let's try now. So doesn't it, if we look here backward, find the loss gradient, and this loss gradient is sent to the next step. We do backward, call this one. What to do with this? So for the first layer, you have to calculate beforehand. Did we do that? Nope.
Previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like Z, so that the activation of the last layer is just your special function, like the sigmoid, applied to Z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case. It's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does, because now we can just keep iterating this same chain rule idea.
Welcome to the stream, by the way. Trying to wrap my head around this algorithm still. Apparently I'm having a really hard time with it. Harder than I thought I would. Let me turn on some music for you again. See the cost. Ever C? We have our A. Our C is affected by A. Go there. Z is affected by those two, B or A. B or W. Find those gradients. Start off by multiplying so we get there, I think. Already have first loss gradient. We need to
be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just...
So how's that one affected by that one? That's affected by that one. Okay. And then after that, just continue walking, I guess. Just multiply. We let's see, fit by A. A factor by C. Z. That one fit by that one. Okay. So basically we just send it the first calculated loss gradient, which is the loss function. We then go to the backward here. So multiply it by two derivatives here. So let's see. Can we bring up Paint? Not sure which file it is anymore, but I've done multiple ones, not that one. Let's try next. Not that one either. Ah, there we go. So we have. Wait, what do we have? We have C. So we need to calculate this and that, I guess, for each step we take. That's a result of that. A is wrong. Y hat. Oops. Which is the prediction. And this else has to be divided 1 divided by n, right? Let's see if they did that math here.
L. Only of the training examples, its derivative.
Yeah. Wait. Okay. Doesn't W. Can't we just do it this way?
Requires averaging this expression that we found over all training examples.
Okay.
And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work.
This is confusing. So what he wrote down there said 0. So what we have here could be written like, hold on. I think del C W L 1 divided by N sum N minus 1 K equals 0 and C0 is multiplied del W L.
Over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work.
Like, we need that derivative, and then when you go to next set, what happens if we want to reach a different one?
The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression,
the predicted values. Okay, so pass that one up. For the gradient of weight, we let's comp this one out. Multiply that. Wait a minute. That's a loss function. We can't just pass the loss, can we? Loss gradient. So loss gradient is wait, is that loss gradient? No. They suggested that we just replace that with the loss multiply by 2. Did their math show? Show me your math. Curious here, what is it we should truly pass? That one's always the same. Cost at 0. I guess that is right anyway. Just pass F1 forward. Derivative to A. But that means minus Y. But that doesn't work forever. So maybe I have to keep multiplying this. Just trying to find the same article again, but it's impossible. This is not going well today. We can... Let's look at the course material again. Compute predictions. Y hat. I equals 1, blah blah blah. Compute backpropagation. Okay. look here then. Just a prediction. LDA 2 LZ LDW Let's predict myself one. That's not what happens with the cost function here. And then we have respect to those. That's why supposed. For propagation, path propagation, we get the L value there. The A derivative of that, I have that. Z is still the times derivative of that. Okay. That gives us a very short answer. Why? What is G now? Situation function. So, sure. And it goes said. So I calculate that. The derivative of that. Okay, so loss gradient. So the loss gradient should be that. But sum them all up and we by themselves. Okay. And for some, 2 times pred minus that's y divided by the length, and let's see that for that. Okay. Okay. So now pass the one on that direction. So have it here, we send it to the first layer. Here. And we'll multiply this. By loss gradient times self inputs times that one. Is this right? The derivative of that one times the input. I think so. And then for this, we just remove that. I believe this will just be a bunch of dot products. Possibly. Then we're gonna have to continue this. So now that we have used there, we'll need to pass it on. Is it just only transpose with the bias gradient? Bias gradient? Sounds weird. Yeah. We'll look at the lower presentation file here. This one. can see all of the information now. Find the first way, so first B. Then to find the next. LT A1. That makes no sense. First step, calculated that. Of this. Horrible. It's going very bad. I'm not sure how to proceed. How's it going for you? Maybe I should take a break, but I'm afraid I might forget everything then, like where I'm at currently. So we take that's the route to said. What's that? So that's the only loss we use right now. That's fine. We are. Ooh. Transposed. Weights. Times inputs. Okay. Loss gradient. Thank you, Dotrom. Oh, it's nice to hear you got my back. Sad. So first loss gradient is just a number, I think. We have loss gradients there. We're reusing it. Delta A1. These are like the presentation files teacher used. Believe me, it was as confusing then as it is now without anyone explaining them. These are the worst slides I have seen. Wait, said. Maybe this is it. Dot product derivative, that one. Set one. Superscript as it's. We have that. That would be. Okay. So we're looking at Sometimes it's input transposed. Okay. So. Hmm? I said a step. So that one is with an activation function. It said, and then we have just really. So, and we here. Yes, that's that one. Times 2. And that one, I guess. Then to be how that one is by. So it's there. That's input X. isn't it? Back gradient. Dot product weight, so it's by gradient. It's off the new weights. Okay. Weight gradients, self dot loss gradients. Weight gradient. Dot loss gradients. Suggests bias gradient equals loss gradient. Weight gradient, self weights. So weight gradient has the same shape as weights. Weights in this case is two-dimensional. Weight gradients for some instances can be larger than that. 2. Take the inputs, which are 4. So what happens there? Update the first weights. The LD set. The LD set. Let's go back. Update loss gradient. No. So this is loss gradient times this output transpose according to that one. Wait, no, that's delta A that the A said. What is A said? Stepper. That is also of the calculated values, I think. Said, yeah. Said is right. A's inputs. then we should have okay. Okay. We have this one, so it's not the same shape anymore. Some of it should probably a dot product. What if we did a dot here? So one output. Wait a minute, so 4 inputs. That will of course give us the wrong answer. So that will have to be divided by n. A. So that would just be a number. A is inputs. Say get one column per neuron. Set is predicted 2. Should have 8 weights. That's not possible with this.
derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of
L. So there's a specific A we're looking at. Then when we go deeper, I think let's flip this. Okay, so now we can get the derivative of the mean square error. So let's pass it the true predictions instead. I do need the predicted values. I don't think so. That's why. Send like this. This. The idea is pass on the loss gradient.
Propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer.
So if we want the A elsewhere, might as well just add that. Okay. So we only need this on once. True and predicted. Or predicted and true. That's better. Pred, and then batch y. Though we also need to find the mean value of this. Rather have that. Send loss gradient. The first one. The second one is just how delta A is affected by Z. So go to this one. Oh, loss gradient and delta A. How del A divided by del C. Calculate here. It's just a stepper. Static stepper of the calculated values. Come that far. And this can be used now. Find, yes, and weights gradient. Inputs times loss gradient, and the bias gradient is just loss gradient. And what we return should be the new loss gradient. Yeah, this will not be correct. So, loss gradient, we know that's a single number right now. Weights as 2. Wait, yeah, there's 2 inputs. Let's go back to paint one. And set dv, just the input. That's no multiplication though. That is multiplication. 2, 1, set weights, 2, 2, because it's 4 weights. It's true, there are 4 weights. Should 2, 1. This mesh broadcast 2, 2. So if you look at weights, no, self inputs, or 2 input. Wait a minute. Maybe. Nope. Never mind. Never mind. get? I only get 2. That should be right. Yeah, it's the output layer. Should be correct. The output layer should have 2 weights. Yeah, because it's 2, 2. Because of the you do that and dot product. Maybe. Wait, multiply. Take the inputs, which are 2. Double that. With loss gradient. No. So the inputs. What's the problem here? Isn't the loss gradient just one number? I think it is. Multiplies float. Non-int. Let's see. Oh. Da, 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 da. Two. So we get 2 for some reason. Take the inputs and the loss gradient. Inputs times loss gradient. Self weights should be 2 weights. Self input. Oh no. Line 70. For instance, say self weights. Minus self weights. Yeah. What will it tell me? What secrets does it hold? How can it have... Wait. Is it the weights? Because the output should only have 2 weights. It only has 2 weights, but it's transposed. Okay. What? The weights. Okay. So do we have to shape this? So when you give the weights, how do you do that? Okay. So could we not really. Tile. What about that? Oh. So it's like 1 weight per neuron. And we'll need to convert this to that format. Does that work? Self inputs. Reshape. Okay. Let's try. Okay. We got further. Oh. Okay. Hidden layer 2 with input shape. one. Is that input? Loss gradient. Is that. Okay, so step has a support for single integers as well. Find step. Let's see. Loss gradient. Wait, I get 2 loss gradients? I think we should get 2 loss gradients. We update loss gradient. I multiply it by that, but maybe if we apply dot product. Perhaps. Nope. So I think I'm gonna end now for today. Because I'm completely lost. But thanks so much for watching, and I